So there's actually a cool analog to lines with the non-homogeneous versus homogeneous differential equations. A non-homogeneous differential equation is like the line y equals mx plus b, where b is not 0. And a homogeneous differential equation is like the line y equals mx. So let's see why this is, and let's actually pick a number. So I'm going to say m equals 2. So this is y equals 2x. I'll actually kind of draw this sort of to scale. And then over here, I'm going to say b equals 1. So this is y equals 2x plus 1. So it's just this line, but shifted up 1. And then what happens? If you've taken vectors, you can think about points on this line as vectors. So you might have learned about vectors in high school. If not, you might have learned about it in Math 126 if you've taken that. If not, don't worry too much about it. So let's see what this point is. Call this 0, 1, 1. Then this is the point 1, comma 2. And you can think of this, if you want, as the vector going from the origin to that point 1, comma 2. Vector is just a something that points in a direction. So it has magnitude and direction. It has a length, has a direction. It can be moved around. This just says move 1 to the right and up 2. So pretty much the same thing as the point 1, comma 2. And then I could take another point on this line. I haven't drawn this super to scale, but let's say this is the point 3, comma 6. If I were to add those together, and this is why I said vectors, because it makes a little bit more sense to add vectors together, but you can do it with points. Then I get the point 4, comma 8, which we notice is also on this line. And I could add these together actually with coefficients here too. So I can take any linear combination of 2 points on this line, and I'm always going to get a point on this line. And why is that? Well, if I called the points x1, y1, and x2, y2, then let's see what happens. They both lie on the line, so they both satisfy the equation of the line. So y1 equals m, x1, I'm going to do it in general, actually, not even just for the value m equals 2. And I get y2 equals m, x2. If I add these two equations together, and actually, maybe I'll even multiply. So I'm going to look at the point ax1 plus bx2, comma ay1 plus by2. That's a linear combination of these 2 points. It's a times the first one plus b times the second one. Then I can do that to these equations, right? I can take a times the first equation plus b times the second equation. That's still going to be an equation. So I get ay1 plus by2 equals amx1 plus amx2, plus bmx2, sorry about that. And then I can factor out an m from the right side. So I'm going to write the left side as is, equals m times ax1 plus bx2. And now I see that this point, ax1 plus bx2, comma ay1 plus by2, satisfies this equation. So I've proved it in general, that linear combination of any 2 points on this line will again lie on the line because it satisfies the equation. What happens over here, probably should not have used b. I'm going to change this to capital B, so it's not the same as the other b. I could change it to capital A as well, but I won't. Okay, laziest way to fix my problem of using the same letter twice. Okay, so now I'm looking at this line, and I could pick, like, let's say this is the point, let's do this in this color. Let's see, y equals 2x plus 1, right? So this is the point 1, comma 3, if I were to put 1 in for x. And then this is the point 2, comma 5. Now if I add these two together, 1, comma 3 plus 2, comma 5, I'm going to get 3, comma 8. But the point on this line corresponding to x value 3 is actually 3, comma 7. So this does not work the same way, not on line. And that's because, like a non-homogeneous differential equation, we have this extra b here. But what we can do is if we subtract, let's say 2, comma 5 minus 1, comma 3, that's going to give me 1, comma 2. I'm just subtracting x coordinates, subtracting y coordinates. that is a point on this line. And that's going to be true for any pair of points on this line. If I take 3 comma 7 minus, let's take something different. This is the point 0 comma 1 minus 0 comma 1. Then I get 3 comma 6. That is a point on this line. And we can show that as well. We can say, let's say we have x1, y1, and x2, y2, this time satisfying this equation. Maybe we'll make them, I'm not doing a great job of making different letters this time. Let's make them capital letters so that we're not using the same variables in the same problem for different things. Okay, they're going to satisfy the y equals mx plus b, so y1 equals mx1 plus b, and y2 equals mx2 plus b. And this calculation is going to be a little easier. I'm just going to subtract these two equations. So I get y1 minus y2 is mx1 minus mx2. The b's are going to cancel, and I can factor out this m again. So y1 minus y2 equals m times x1 minus x2. And behold, the point x1 minus x2, comma y1 minus y2 is a solution to the equation y equals mx, which is the corresponding line through the origin, or thinking in differential equations terms, the corresponding homogeneous thing. So that's cool. And hopefully this helps you geometrically to see why some of the homogeneous, non-homogeneous stuff works.